All right. Welcome everybody to today's Corundum developer meeting. Thank you very much for tuning in today. All right. So basically the main thing that I have for today is just more status updates in terms of what's new and what I've been working on, what's coming up next. All right. So status update summary, just rounding out new device support, all that's now live in the main upstream repository. All the changes have been pushed along with I think a couple other kind of follow-up nitty-gritty changes. And the PCIe flow control stuff I think is all squared away at this point. Seems to be doing what it's supposed to do. Then I've been working on some new features as well. So Q pointer write back I've been working on, and then the next thing I'm going to work on is batched completion write back support. So the Q pointer write back it works in hardware, but there's a couple things to talk about, which I got slides on that in a minute. And then after I get the completion write back support, then I'm going to work on variable length descriptor support using some of the stuff I have to develop for the write back support and the completion write support for the variable length descriptor support. So that's why I'm doing things in that particular order. And then also you'll see in the slides in a few minutes. And then everything else is just carryover stuff. So new device support, 250 SoC design is now live. The Intel Stratix 10 DX and DE10 Agilex designs are now live as well. So we've got P-tile and E-tile support, lots of new devices. On the everything involving the E-tile, I have 10 gig, 25 gig, and 100 gig working. There's something weird with the design on the Stratix 10 DX at 100 gig, so I need to get that sorted out before I put that example design up. PTP has some issues with the E-tile though. There's a weird issue where if you saturate the 10 gig or 25 gig link, then in the TX direction, then the RX timestamps are screwed up. Haven't gotten to the bottom of that yet. And the 100 gig, in order to do anything with PTP, you got to do this complicated calibration routine. So I'm going to back burner all that for now, and we'll circle back to it at some point. Basic functionality is working at this point. So that's a start. Then in shim PCIe flow control, like I said, with the addition of all the FIFOs in the shims, this kind of screws up the way flow control was implemented before. So what I've done is I've moved all the flow control out of the DMA engines and into the adaptation shims. So it's done for everything, except I haven't implemented anything on the RX side in the Agilex devices. So with UltraScale, the split between completions and incoming requests is done inside of the hard IP core. So the hard IP core handles the receive flow control, basically. For the H-tile, they don't give you any way of controlling that. You just have one RX interface, and you just got to deal with it. For the P-tile, there is a way of exerting back pressure separately on various types of incoming TLPs. I haven't implemented that yet, but it basically will operate the same as H-tile in the time being. So for now, I'm going to back burner that because I don't have any applications that need that. So I'm not going to spend any more time on that in the near future. So that's going on the back burner. And that rounds out the PCI Express side of things. So moving on to the Q pointer write back. So I went ahead and implemented this on top of the current descriptor and completion handling components just to get an idea of what the performance looks like and to see if there's any pitfalls that we're going to have to address. Just make sure everything looks fine. So the idea is that right now the Q pointers are read from hardware via MMIO. And that's slow because MMIO's CPU issues a read operation that's got to go out over PCIe. The device has to respond, has to come back. The CPU can't do anything during that time. I don't think anyway. I'm not sure what the CPU does while an MMIO operation is taking place. Could just be waiting for it. Maybe you can run something else on there while that's taking place. I'm not sure. Anyway, it takes a while for that read operation to come back, and that's not great from a performance perspective. So the idea with Q pointer write back is to use a DMA subsystem to push the updated Q pointers back into host memory. So you just, from the standpoint of the driver or the user space software, you can just read from host memory somewhere to get the updated pointer. So better from a performance perspective, hopefully. That's the idea. Now, previously, I had already implemented some immediate write functionality in the DMA engine. So using this, we can pretty easily add support for Q pointer write back without having to, write the pointer out to an internal memory and then ask the DMA engine to transfer it, which is what you need to do for larger blocks. So the status on this is that the Q manager logic has been updated, the driver's been updated, tested it in sim, tested it in hardware. Everything works, but the performance is not very good. And I got a couple of graphs on this in a minute. My current hypothesis is that in order to get high performance, you need interrupt coalescing. And MMIO has been slowing things down enough to kind of act like interrupt coalescing is working. Except I haven't implemented interrupt coalescing yet. So by implementing Q pointer write back, we're losing the slowdown effect of the MMIO reads, and that is causing some performance problems. So in order to bring back the performance, I now have to go implement interrupt coalescing, which with the current setup is not super straightforward. So I'm going to do the batch completion write first before the full variable length descriptors to implement interrupt coalescing and see what the performance looks like. So let's take a look at these graphs that I have here. So this is the baseline. This is on the Alpha Data FPGA board. This is everything's all defaults here as it is in the repository. Write back off, and we're using MMIO to read the Q pointers. And this is just running with 9K MTU because the differences are a little bit more obvious with this than with the 1500 byte MTU. All right, so that's the baseline. Now, what I did is I went ahead and I turned on write back. So this is inside the driver. We allocate all of the memory regions where the pointers are going to be written back. We write the locations of those into the Q manager logic such that the hardware can actually write the pointers back. But we're still reading the Q pointers via MMIO. So the only thing that's being changed is that the hardware is writing all of this additional data. And the result, next slide, there we go. There we go, okay. I don't know why this is being slow. Okay, there we go. The result looks like that. So it's similar, but there is a slight difference in performance. So this is with write back on, but we're reading with MMIO. All right, so we can see over here that there is a small drop, or there was a drop, but it was over here somewhere. Now it's moved back here in terms of the RX performance. And then these have shifted a bit. The RX performance, when TX and RX are running at the same time, RX performance has dropped a little bit and TX performance has gone up a little bit. So I'm going to switch between these two. We can see that a little bit more clearly. We can see that that little dip in RX performance when RX is running in isolation, that moves from what, around like 10 or 11 Qs, that moves down to like 7. So that's problematic. And then we can also see that that change where the RX performance drops a little bit as well. When things are running simultaneously. Okay, and then the next thing that I did, so that's not really a big change. All this extra data being moved doesn't really have a huge impact on performance. The other thing I'll mention is that the way this is set up, every time a pointer gets updated, it gets written back, which means we're probably doing a lot more pointer writes than we need to necessarily. We batch the completion writebacks and the event writebacks, then we can batch the Q pointer writebacks and reduce the amount of traffic. But that's not implemented here yet. Okay, so that's the first graph, or that's the second graph. Okay, and then the third case, I turn everything on and whoa, things change significantly. The idea is here, we're reading the Q pointers out of the NIC, or we're not reading the Q pointers out of the NIC, we're reading the written back pointers out of host memory. And this has a significant impact on performance. We can see the RX performance drops quite a bit over what it was. The TX performance doesn't seem to be affected at all. that blue curve is doing exactly the same thing. And the transmit performance when both TX and RX are operational has increased. So that this is telling me that there's like, you know, the fair sharing thing. I'm not sure exactly what resource we're contending for here, but the TX performance is somehow stealing from RX. So that's definitely something that's going to have to be looked into. The interesting thing that I've noticed on all of these, going back even earlier, is that if you look at kind of the difference between, if you're running TX and RX at the same time, you can draw a line here. It seems like around 70 gigabits per second or so, and they always seem to be centered right around that line. Same kind of thing here, about 70 gigabits per second. I'm not sure what the significance of that is, but it seems to hold up pretty well on all of these curves. So I'm not sure if that's something about the network stack or the software or something about Corundum or something about PCIe, but that's an interesting observation there. So anyway, the takeaway from this is I think what I need to do is go and implement the interrupt coalescing, and hopefully that will restore some of this performance here. So as a result of that, now that I have the Q pointer write back working, what I'm going to do is work on batch completion write support. And this is sort of the converse to the variable length descriptor support in terms of how the queue management components are going to be reworked. But the idea is pretty straightforward. Writing completions individually is not very efficient because of the PCIe TLP header overhead and whatnot. We're sending a bunch of 32 or 64 byte packets. That, you know, that's not great from a throughput perspective. But if we batch them and write them in blocks of, you know, 128, 256, 512 bytes, that ends up utilizing the PCI Express link more efficiently. So we have less overhead. And then if we're going to be batching these, then we can also at the same time, when we issue the block write, we can also issue events, IRQs, and Q pointer writes concurrently, which will reduce the number of these events, IRQs, and Q pointer writes. So this effectively means we're doubling as interrupt coalescing. And then we can do this based on either, you know, the number of completions that have been stored, spooled to be written. Once we reach a certain number of those, then we can fire off a write back. Or we can do it based on a timeout. So if there's just one that gets queued up after, you know, so many milliseconds, so many microseconds, whatever, we can fire off a write back. And that can potentially be configurable. And then we can also trigger a write back on eviction, because the idea is we're not going to have all that many slots for this. You know, we might have several hundred queues, but maybe we only have, you know, 16 or 32 write back slots. So potentially we're going to have to, you know, evict one of those. So when we do that, then we would also trigger the write back. So right now I'm working on kind of the initial implementation of what this is going to look like and how the pieces are going to fit together. So that's one piece. The next piece that we need is, so once this is operational, then I'm going to be moving on to variable length descriptor support. So I haven't talked about this in depth in a while, so I'm going to go into a little bit more detail today, just so we're all on the same page again. So variable length descriptor support, the idea is to provide more flexibility to the descriptor management subsystems such that we can implement more complex operations, and we can also carry out operations more efficiently. So right now, the queue management logic only handles fixed length descriptors. And in order to implement variable length descriptors, we need to implement basically more simplified queue managers, which just store the queue state, but don't do anything else, and then implement more complicated descriptor fetch and header parsing logic, which will read descriptors in blocks instead of reading just single descriptors. They could read, you know, 256 or 512 byte block, and then parse the descriptors out of that block and hand them off to the logic that's making that request. And potentially we can also add some extensions to this to support things like LSO and TSO. And status on this, working on supporting components, basically. I'm hoping that the batch completion write support, once I get those pieces put together, it's going to be somewhat similar at a high level to what needs to be done for variable length descriptors. And I'll be able to kind of reuse some of the pieces for that. So, all right. So the current descriptor format, getting a little bit lower level, looks like this. It's 16 bytes. It's got a 64-bit address, 32-bit length, and then 4 bytes of other stuff, basically. The nice thing is they're small, right? It's only 16 bytes. So if you're sending simple, small packets, it's pretty efficient. But because it's fixed length, if you need to use scatter gather, then what we effectively do is just send blocks of several of these. So it could be 4, it could be 8, something like that, which allows you to send more pointers, but you have extra overhead for small packets because you're always sending the same number of pointers, which, you know, that's not so great. So can we do better than that? Well, yeah. My thought is to kind of split the descriptor format into 2 pieces. We have the descriptor framing format, which indicates how big the descriptor is, and from the actual descriptor format, which has all of the additional fields. As a result, the queue management logic and the descriptor fetch logic only has to be aware of the descriptor header in terms of the framing format. It doesn't need to look into the complete descriptor. So splitting the framing from the contents, that means that the descriptor fetch logic, it only has to look at the first couple of bytes. The rest of the descriptor, you can just process that and hand it off without having to do anything else. All right. So the idea here, so we have a descriptor header with a length and a type. Length indicates the size of the descriptor in terms of 16-byte blocks. So 1 for the length would be 1 block, 2 would be 2 blocks, so on and so forth. With an 8-bit field, that means we can have a 4096-byte descriptor, which is huge. Probably won't support them that big, but this format supports that. And then we have a 1-byte type field to support multiple descriptor formats. We can start out with a simple one. We can implement more complicated ones later as necessary. So this is kind of the framing format idea. And then for a descriptor format, which has additional fields for performing more complicated operations, this is kind of what I'm thinking. We have the descriptor header. We have flags, opcode for sending and receiving data. We didn't really have many operations, but once you bring RDMA to bear, if we want to implement RDMA operations, we need a bigger opcode field to tell the NIC what to do. Then I have a couple of additional fields here, data segment count and inline data length. The idea here is that the descriptor can contain several data segments, which contain the length and address pairs for blocks of data. And then following those, we can have some inline data, which will be effectively a packet header or maybe an LSO header, or it could be a complete packet sitting inside of the descriptor queue. For small packets, it might make sense to do that if we're just sending a few bytes instead of performing a whole separate DMA operation to read the packet data. We can just stuff it right in the descriptor. So that's basically what this is looking like at this point. I haven't implemented this yet, but this is kind of what I'm thinking. It seems like this is going to support most of the operations that we need. Another aspect of reworking the this subsystem is that we also need to think a little bit about queue state storage. So every queue needs to have some piece of information sitting in memory on the FPGA. Corundum is designed with the idea of supporting tens of thousands of hardware queues. So being able to store that many queues efficiently, you got to make sure that the queue state is small and you're spending bits where it makes sense to do so. And I need to take the existing kind of set of information and add several fields. So write-back pointer is necessary for the write-back support. If we want to implement SRIOV at some point, we need room for a virtual function index. And then if we're going to implement LSO at some point, we need to be able to store the LSO offset, because that'll have to be effectively saved and restored if we interrupt an LSO operation. So that's the difference between LSO and standard descriptors, I suppose. LSO, you have a single descriptor that codes for multiple packets effectively. So if we send the first couple and want to pick up where we left off later, then we have to store this piece of information for a while. But we can potentially reclaim a couple of other fields. So the status of this is I've implemented the queue state storage module. I don't think it's quite complete yet, but it's looking good. And also the other nice thing is that I think we can do this in such a way that we can reuse the same module for both normal transmit receive queues and for completion event queues, unlike the current setup, which uses separate modules. So I think it's similar enough to where the differences can be implemented with a parameter. All right, so here's what the current queue state stored looks like. We have a base address, head and tail pointers into the queues. We have, or into the ring buffers, we have the completion queue, event queue, or IRQ index as depending on the queue type. Then we have log queue size, log block size, arm contiguous for the completion event queues, enable operation index that's used internally for coordinating multiple operations, and then total here. So these all fit into 2 ultrarams. So ultraram is 4096 by 64. So 2 ultrarams will store the state for 4096 queues. That's pretty efficient. But a couple of these fields can go away. So the descriptor block size, or the log block size, this is related to the current kind of hacked up implementation of scatter gather. So with variable length descriptor support, we don't need that. Then op index, this is used internally by the queue manager to manage outstanding operations. Since the queue managers are not going to do that anymore, and we're going to handle that in the descriptor fetch logic, that one also goes away as well. So that gives us, 8 bits over here, 10 bits over here, not very much. So I started looking at some of these larger pointers, like the base address fields, like do we actually need all those LSBs? If we force an alignment on here, then we can steal some LSBs and use them for other things. So after quite a bit of head scratching, I came up with this for the current setup. So by shrinking these to 52 bits and forcing a 4K alignment into the rings, which I think is fine because every time you make a request from DMA alloc coherent, it's going to be at least a page, which is going to be 4096 bytes. So that shouldn't be an issue. And then we can reuse some of those LSBs. So we still have the producer pointer, consumer pointer. I renamed these to be a little bit, less confusing, because head and tail, there's kind of 2 different conventions for how you can use those, and they're exactly opposite. So producer and consumer, that's a little bit more clear cut. And then we have the CQ, EQ, IRQ index. I was thinking about maybe making some of these larger, but 16 bits I think is pretty good for a ring size. That's 64K entries inside of that ring. I think if you have that much data in your ring, then something is not working correctly. CQ, EQ, IRQ index. You could potentially make this larger, but you got to actually implement those queues in hardware. So 16 is probably about the max I think you'll be able to implement in hardware. And if we are going to implement more, then we're probably going to have to rethink this whole, we're probably going to have to use a different method for keeping track of all this information. Log queue size 4 fits very nicely with the 16, right? 2 to the 4 is 16, so that's fine. And we have these same bits here. I added 1 bit here, so we have an active bit and an enable bit. The enable bit is controlled by software, the active bit is controlled by hardware. So every time hardware is working on a particular queue, it'll set the enable bit. And then most of these fields here will be read-only when either the enable bit or the active bit are set. That's kind of how that works. Let's see, what do we have down here? Then we have the VF index. I was able to fit 12 bits for VF index, which I think is about the max you would ever need. LSO offset, we can fit 16 bits in here for the TX and RX queues. And then the write back address, we make that 58 bits and force a 64 byte alignment, then we have exactly 192 bits, which is 3 ultrarams. And then for the CQ and EQ, it's 178. So that fits nicely. And then the other fun thing is that if we turn off the write back address and we shrink the VF index to 6 bits instead of 12, then this fits into 2 ultrarams, 128 bits. So we can actually make that controlled by a parameter value. If you turn it on, then you get write back support and you get 12 bits of VF index. If you turn it off, then you lose 6 bits here, you lose the write back address, but you use, you're back to the same footprint that we have now in terms of ultrarams. So that looks pretty good to me, I think, in terms of the queue state. All right, that about rounds out all of the main updates that I had for this week. So management software, that's still to do. Once I get some more stuff squared away, I'll switch back over to working on that, unless somebody else wants to hammer on that. 10G, 25G switching, this is basically blocked on the software at this point, although there are a couple of updates potentially to be made for handling TX packets through the application. I also have a clock info register block on the to-do list for, for diagnostics. And then I'll bring back my to-do list for the stable release here. I have very blank Descriptor support on here. I'm now working on that, so hopefully we'll be able to get that knocked out relatively soon. All right, so that brings me to the end of the updates that I have for this week. If anybody has any questions or comments, fire away.
I got a quick comment. Or did you say you turned or used MMU? You had the IOMMU off? We typically turn that off when we do latency tests. When you were saying about the MMIO.
Oh, the MMIO operations? That's a
Yeah.
good point. Yeah, I have not tried screwing around with that. Possibly that would have some impact on performance.
Yeah, probably not for bandwidth. We use it for latency sometimes, right? Depending on.
Right. Well. So if you look down here in my my hypothesis about the interrupt coalescing being needed for high performance, but potentially the slower MMIO reads are sort of emulating that that effect, right? By you perform an MMIO read, but it takes a microsecond or something to get that response back. In that time, maybe a couple more packets have shown up.
Yeah.
So it's possible that if we turn off the MMIO, then or the MMU, then maybe the performance would drop because we're not getting as much delay out of the MMIO read. So it's kind of an annoying situation to be in. But if we go take this, and if I can get the batched completion write support working and actually implement a more sensible version of interrupt coalescing, then that could solve this particular issue. That's the hope anyway. If it doesn't, then I don't know. But yeah, so that's definitely something worth trying. I haven't actually done any playing around with the MMIOs or with the MMUs on these things. So I guess one thing is that I've been using these AMD EPYC machines quite a bit. Just not necessarily recently. Recently, I've been mainly using this Xeon-based machine that I have here with the Xeon scalable CPUs. But with the AMD ones, I think I tried turning the MMU off, or at some point, not the MMU, but the IOMMU off at some point, and it either didn't let me turn it off or something strange happened. But I think the Intel machines are a little bit better about turning off the IOMMU and doing useful stuff.
Yeah. So, we normally do it just the command line parameter kernel, right? Not even
right.
BIOS setting or anything.
Right. So. Right. Yeah. No, I think I've tried that before on the. I know we do that occasionally on the machines in the CSE building for various experiments. We'll turn off the IOMMUs for performance. I think, as I recall, that was one of the things that I tried on the AMD machines because I was getting terrible performance. I'm like, well, maybe if I turn this off, things will get better. And I think I turned it off and things got worse. So I'm like, okay, never mind.
Mileage may vary. And then the other. Well, go ahead.
Yeah.
I just had another quick one about, you said you were looking at, changing the queue state for VF or for virtual or SRIOV. Did you mean also you're going to support, or do you already support, physical functions, the PFs?
We don't support multiple functions right now. So I guess VF is more like PF and or VF index. Okay. I've had a couple people asking about SRIOV support. And so I've done some thinking about what you would need in order to actually do that. So one of them is that we're going to have to add function numbers onto all sorts of internal interfaces. So I think like all of the AXI Lite stuff, I might need to go rework all of my AXI modules to add a T user field, which we can then stuff a VF or PF number in. And then we can use that to determine who can see, which queues and whatnot. I have not totally figured out exactly what that's going to look like, but the idea is, is there a way we can implement multiple functions, physical or virtual, without, totally ballooning the resource consumption
Right,
and,
right.
still provide the benefits of something like SRIOV. So kind of my thought is you pass the VF number along with all of the, AXI light operations, and then where you're actually performing the operations, you can check to see if that VF is allowed to access that. So for the queues, if the VF index doesn't match, then you wouldn't be able to read or write anything. Or maybe you could see if it was enabled or not, but you wouldn't be able to read, any of the pointers, for security reasons. You wouldn't be able to write anything, obviously. But if the VF number did match, then you have control over that queue. You can do whatever you want. So using this setup, the PF would be able to write into the VF index registers in the queue control modules and effectively assign queues to different VFs. So that's kind of the idea here. We have to have the queue state there in order to actually implement that. So actually implementing it is a different story. But I'm trying to think down the road, like, okay, if we wanted to do this, how do we do it? What's needed? And then I guess obviously another aspect of that is that VF number will also have to be passed with the DMA engine so that the IOMMU does the correct thing, because all that's based on the function number, either VF or PF or whatever.
Makes sense.
Yeah, so it's at some point it would be cool to have SRIV operational. It's just basically a lot of this stuff I work on based on my needs and the research project that we're doing at UCSD, what we need for that. So SRIOV is unfortunately not something that we need. So I have not been, actively spending a lot of time implementing it, but I do recognize that it's an important feature that other people would like to see. So I have been thinking about, how can we possibly implement that? What are some of the stumbling blocks to make that work? So I guess MSIX was another thing, right? That was SRIOV requires MSIX, but we were also running into performance issues with MSI. So having MSIX, you get more channels, you get it alleviates some of the performance problems we were seeing, and it's necessary for SRIOV. So this basically adding these Q state bits and switching to MSIX, we've now taken down 2 of the major roadblocks in the way of supporting SRIOV. So yeah, once we get it working, that'll be pretty cool. But
yeah, that'll be nice. That's all I have. Thanks.
All right. Does anybody else have any questions, comments, concerns?
I also have question about DMing the queue states. I think you mentioned something like not for every packet, sending it not for every packet, but for every n packets, right? Or time, when timer is.
Right. Yeah. So my thought with sending that back the queue pointers, writing those out into host memory is basically just grouping everything together, right? The block write for the completions / events, the event / IRQ generation, and the queue pointer write. We do all those kind of at the same time, if that makes sense. So we can queue up several packets or several completion and completions or events for a particular queue into an internal buffer. And then either once we filled up the buffer, or we have a certain number of these in the buffer, or a certain amount of time has elapsed, then we can trigger not only a write back of the actual completions, but also the generation of the event or interrupt and the queue pointer write back. So that'll reduce the number of queue pointers that are written back. That'll reduce the number of events and IRQs that are being generated. That's kind of the idea. Does that answer your question, or?
Yes. I was asking about this, and so we'll get rid of TLP overhead, right? Hopefully,
right, yeah, we'll reduce it. We'll reduce it. You always have to pay the overhead every time you send something over the bus. But yeah, the idea is that by sending larger blocks, that there's less overhead. All right, does anybody else have any questions or comments? I know MLE opened up a couple of pull requests, at least one pull request recently in terms of some I2C stuff. I don't know if
exactly.
we talk about that at all.
Yeah, well, yeah, I guess it's kind of an early state, as you mentioned, that to actually fix this in a good way, we might change how we actually use this interface or provide this interface internally. Not sure. I guess I'll have an internal discussion.
Right. So I guess the gist of it is that for SFP modules, not SFP pluses, but you go back another generation SFP modules, to access more than, I guess, 256 registers, they use multiple I2C addresses. That's the gist of it, right? So you have to change the, you have to access a different I2C device address to get that upper set of registers.
I actually see this happening. Yeah, that's the problem. But I see this happening with SFP Plus modules as well. So that's why we came across it.
Okay. Be interesting to just put some notes together as to which modules we're seeing this behavior on.
All opticals that I got across for now.
Interesting. Well, let me think. What modules have I poked into here so far? So all of them you've seen multiple I2C addresses. Interesting.
No, it's just the optical information. So like the diagnostic part.
Right.
So if you use direct attach copper, there is no problem because it doesn't provide this much of information. But if you have optical modules, you have all this alarm settings and transmit power and such stuff.
Right.
And that's all part of the upper addresses. And to use this properly, actually it was partially already encoded in the driver, but yeah, it just hasn't been passed through the whole chain.
Right. So okay. So I guess I can shed a little bit more light on that. Initially, when I implemented the API for accessing the modules, there was no mention of like I2C address or anything like that. That's a newer ETH-tool API that was implemented at some point that has those additional fields. And the reason they did that is because there's so many, well, at least as far as I can tell, so there's many different optical modules, and they have different idiosyncrasies in terms of how you access them, right? So it seems like for SFP modules, they use multiple I2C addresses. For SFP28, QSFP28, they use a page register in that first 256 byte window that you have to write to over I2C in order to look at the upper pages. So just to complicate things. So
yeah, that's right. They changed it like 3 times or so. There's 3 different standards associated with this interface.
Right. Yeah. So I ran into that when I guess there must have been a change in ETH-tool where it started reading out those higher order registers. Probably coincident with the API change, so it actually could request those higher registers. So I had to go rewrite everything to support writing to that page register. And then so the way the page register works is I guess you can access 256 bytes worth of registers directly. The lower 128 is always fixed. To the upper 128, there's, I guess, 4 different kind of banks that you can look at potentially. So you write to one of the locations that selects what you're looking at in terms of the upper 128. This is on the QSFP28 and I guess SFP28 modules. And most of what I have running around here is like, I don't have much in terms of 10G optical modules. So I guess I didn't run into the this different address problem. But yeah, so I had to do some work to implement the new APIs and then also write to the page register. So I'm assuming that there must already be some sort of locking in place guarding the state, because if we're writing to this page register on the actual module, you don't want to have multiple operations trying to talk to the module concurrently if they're fighting over the page register. So I'm assuming that Linux will have some sort of a lock somewhere, but I haven't gone spelunking to try to confirm that. So that possibly that could alleviate the need to implement additional locks, but
okay, yeah.
But that's just
Yeah,
one of the issues, right?
Yes.
The other issue is the addresses, and that's a different story. I don't know what to do about that.
Yeah, well, if there's just one, but I guess there is potentially multiple ways, but if there's just one way to actually get to this path where this I2C client is used, and if this one is protected, then everything is fine, I guess. Then we can also kind of on the back change this address. And yeah, I guess that would be fine. I'll have another look and I'll have another discussion with Joachim once he's back.
Right. Yeah.
And then we'll see. I just wanted to already open this and maybe we can use this as kind of as an initial workaround and then see whether we can come up with a proper solution.
Right. I mean, the flip side is, maybe it is the most straightforward, method. There is definitely something to be said for keeping things simple. If it's simple and it works,
yes,
you might as well.
Then that's fine. Yes, that's right.
It's just changing that somewhat internal address field seems like that's a bit of a hack. I mean, I don't know what changing that field does in terms of how Linux handles things. Could be just fine.
Yeah.
I don't know.
Not sure. So that's something I want to go through with Joachim. He has much better knowledge about these kinds of things in Linux.
Right.
I just was able to track this down and fix it. And I don't know if there is some damage that I put into other subsystems.
Right. Yeah. I mean, probably not anything else in Corundum, because the only thing that's used for is ETH tool.
Yeah.
That's the only thing that talks to those transceivers right now. Eventually, the idea is that goes through the soft core, and the soft core could potentially poke some other registers. Like commonly, if you have a QSFP28 and you want to run it at 10G, you have to poke a CDR register to turn off the CDRs, so it'll actually run at the lower rate. So, potentially the soft core will poke at stuff like that, and then it won't be going through the I2C subsystem. So we can just directly, implement commands for accessing, such and such address and whatever. So the other thing that got me thinking about, though, is I know Xilinx and some other companies have, they don't provide direct access to the I2C interfaces to the optical modules on whatever board. So like the U50, the U280, I think I've seen a couple Intel boards that are set up this way as well. All the operations have to go through the board management controller. Does the board management controller firmware support accessing any address other than hex 50? Don't know. If it doesn't, then you can't put it. Then you can't put one of these SFP Plus modules in there and be able to talk to it. I thought you were only seeing this on SFPs. I didn't realize SFP Pluses were also doing this. So that's interesting. If it's SFP Pluses, then it's definitely something that needs to be addressed. And I should probably, if we have a few modules in question here, I should probably raise the issue with Xilinx. And I think it might have been Silicom as well that has one of their FPGA boards may also be set up this way. So I'll ask them as well.
So we'll have one LVO card somewhere that I can dig out and see what happens if we put in one of these QSFP Plus to SFP Plus adapters and then just use one of these modules.
So, right. So for the U200 and U250, there's no problem because there's a direct connection So I think you guys said you might have had a U200. It's only the U50 and the U280 and possibly their newer single slot cards that that have this issue. But yeah, the U200, U250, and like the VCU 1525, those three cards are all just a direct connection, so no problem at all on
Okay.
those.
Yeah, then I guess
Although
we can't reproduce this.
I guess it depends on how the so one thing I need to look at on those is I think the little CMS IP core may also have the ability to interface with the oh, I think that's just for the sideband control signals, actually, not I2C. So the little CMS IP cord has a few kind of IO pins, and it varies a little bit depending on what card you put it on. I think on the U200 and U250, it has a couple of IO pins for talking to the optical module, which you can connect or not, depending. I think it's like for LP mode and reset. I think that's what the pins are for there. But I don't think it has I2C connection. I'll have to take a look at it. It's been a while since I looked at that.
Yeah. So in any case, we only use 10G modules, so it's definitely SFP plus. And
right. But the key point is you're seeing this issue with 10G modules. Yeah, right. I don't have many 10G modules bouncing around. I have definitely put 10G modules and SFP28s and DACs into boards using the adapters. So the adapter doesn't do anything to the EEPROM or anything. It just passes that connection straight through. But yeah, well, yeah, so I guess the other thing is I don't think I have anything implemented in the driver right now to talk to the board management controller on the U50 and the U280 in terms of interfacing with the optical module. Part of the reason for that is I think I need to update the BMC firmware on those cards, and I haven't figured out I haven't had time to sit down and figure out how to do that yet. So it's possible that that support isn't even there on the cards that I have at the moment. So I wouldn't be able to test that. That's something to circle back to later, I think.
Yes.
It just got me thinking about that. I'm like, I think their documentation only says that it provides access to address 50, which is a problem if we have to access address 51. So
yes, it is. Yeah, other than that, I just have another question, not directly actually related to Corundum, but maybe related.
Yeah, sure, fire away.
I guess you're moving to the Intel-based boards anyway, right? Because that'll be your target boards.
Well, we are using Intel boards for one particular experiment, yeah.
Right. So are you planning on adding iScan and iBird features on these as well, using the transceiver interfaces for this, which I guess are Avalon memory map based? Okay.
At some point, yeah. At some point, we definitely need to be able to poke at that. But as for when, I need to get it running on the target port first.
That makes sense.
Timing closure is a problem. So once I get that squared away, then yeah, at some point we'll circle back to that. But yeah.
Yes.
I did take a look at the documentation for the, I guess Intel calls it ODI, just to kind of get a sense
exactly
of what it looks like and how to do that. It looks pretty similar to iScan. You kind of set up a measurement and then you fire it off and then you wait and check a different register. When it's done, then you can read out an error count. It's same kind of thing. Hence why I was trying to implement stuff in a generic way, such that we can request measuring a particular point, and then later on get the result of that and then start a different point. So that seems to be a pretty generic way of doing that, and that should work on anything that supports this type of feature, at least in terms of what the user space tool is doing. But yeah, so if you guys wanted to work on that at some point, that would be great. it's at some point I'll need it, and if you guys don't have it working, then I'll have to implement it. But you know, that's probably a little ways down the road. So I don't know how important it is for you guys in terms of time.
I'm thinking to put something together separately. We're not being part of the production design for the Intel board, but for the bring up.
Right. Okay.
So I guess the most important piece missing right now is just a bridge from Axelite to Avalon memory mapped. So the question actually is there something out there that you know of we could use for this? So I didn't find anything, just, well, there is one core, I guess, from Xilinx, which we can't implement on Intel devices, obviously.
Intel really doesn't have any Avalon to AXI conversion, even for their...
Well, this way, yes, but not the other way around.
Okay.
So there is no, or at least I didn't find any Axelite slave to Avalon master.
It's like I thought their SoC parts had a lot more AXI stuff going on, so they would have more of these infrastructure components. Well, we might need to write something. I mean, it depends on what you're doing. So for so I was going to treat it the same way I treated the DRP interface. So we have on Corundum we have a register block that, well, it's not even AXI Lite, it's that register interface. Simplified register interface set of connections on one side, and then it's kind of an indirect operation. So you have address, data in, data out registers, and then you can poke those to perform operations over the whatever's on the other side. So that could be, you know, DRP, that could be AXI Lite, that could be Avalon. You know, so we can make a module like that for interfacing with these guys from the driver or from the soft core or whatever. So that's one option. For implementing this under XFCP, which I think you mentioned that as well as something you were thinking about.
Yes.
Let's see, what did I do the last time around? I guess I had. So when XFCP was put together originally, I was using Wishbone for everything. This was before I started using AXI Lite for memory interfaces. So if I do right now, exactly. I'd probably be using AXI Lite. So I guess for that one, I had some Wishbone to whatever bridge modules that I was using. So
yeah, there was a Wishbone to DRP that you're using for iScan.
Right, yeah. Yeah, so my guess is it wouldn't be hard to do, you know, the same thing for Avalon. From looking at how the protocol works, it looks pretty straightforward because I have a little state machine that I use for poking at the reconfig interfaces on the transceivers to make sure equalization is running. So yeah, for that, so I'm somewhat familiar with how Avalon works there. So yeah, I think it should be just a handful of lines of code to adapt that. I don't have any code lying around I can just give you, but because I haven't had a need for that. I haven't done a whole lot with the Intel devices, you know, really at all. So
okay, yeah. So good to know.
So then getting down and doing lower level stuff, then yeah, we'll definitely have some more Avalon stuff to deal with. But yeah.
So then we'll start poking at it, I guess, and we'll share the code once it's working.
Yeah, sure. Yeah, and I definitely recommend if you get it working, you know, if you're working on bringing up the ODI stuff, it might make sense to do, you know, the separate setup in XFCP first. You can get the kinks worked out in Python instead of in C, just to make things a little bit simpler.
That's exactly the plan. Yes.
All right. Sounds good.
Cool. Great. Thanks.
Yeah. Does anybody else have any questions, comments, anything? Nope. All right. Well, going once, going twice. All right. Well, I guess we'll call it a meeting for today and talk to all you guys in 2 weeks.
Okay, thanks a lot.
All right. Take care. Talk to you.
Thank you.
Goodbye. Thank you.